Alright, hello and welcome to our reteach for Newton's laws. I will be covering a couple of the questions from the review. I've cut some out and I've highlighted the ones that I'm going to be talking about. I'm generally going to try to hit every single concept at least one time. But considering the unit we are in right now when you are listening to this, we already should have gotten a little bit of this, hopefully reinforced going through friction and forces and angles, because essentially it's just the same thing with a little bit less stuff. But just in case, there's this reteach for, yeah. Alright, so let us start then with net force. So, 10 kilogram object is slowing down from 24 meters per second to a final velocity of 9 meters per second in 3 seconds. We want to find the magnitude of the net force acting on the object. So, a couple of things. Anytime we are dealing with velocities, times, things like that, we're going to be using kinematic equations as part of our calculation. But first things first, it wants me to find the net force. That'll come from F net equals ma, Newton's second law. And to do this, I know the mass of the object, it's 10 kilograms, but I don't know the acceleration of the object. However, because I have these kinematic information here, I can calculate the acceleration. So I have initial velocity, final velocity, time. I'm solving for acceleration. We're going to use the first one on the kinematic equation sheet. Vf minus Vi, or Vf equals Vf plus At. But when we rearrange it to solve for acceleration, we're going to get Vf minus Vi all divided by time will give us the acceleration. So I can do that here. We're going to get 9 minus 24 all divided by 3 equals my acceleration, and if I plug this into my calculator, I get negative 5 meters per second squared. So that's my acceleration. I can plug that into my equation. So F net is equal to 10 times negative 5. That's going to give me negative 50 newtons, or 50 newtons to the left is my net force. So this is one of the net force equations we use, which is just F net equals ma. The other one, which we'll get to in a little bit, comes from the free body diagrams that we draw. But that's our net force question. Next up, Hitchcock has a mass of 100 kilograms on Earth. We want to find what his mass is on the Moon, where the force of gravity is approximately 1/6 that of Earth. Here's the thing. Mass and weight are not the same thing. Mass is a measurement of material, how much of a thing you have. Whereas weight is the force of gravity on a mass, on matter. Mass is matter, and weight is a force. Weight changes based off of your location. If you go to the Moon, you weigh less. But if you go to the Moon, there's still the same amount of you. Your mass does not change based on location. Mass stays the same regardless of where you are, unless you physically change the mass, like cut it in half. So, how much is his mass on the Moon? It is the same. It is 100 kilograms. It does not change. Mass does not change. Number 4, though, what is his weight on the Earth versus on the Moon? Weight will change. So if we want to calculate weight, it's Fg equals m times g, mass times acceleration due to gravity. So on the Earth, that is going to be F equals 100 times 9.81, which is going to give us a force of gravity, or a weight. Remember, force of gravity and weight are the same thing, of 981 newtons, versus on the Moon, it is 1/6 that of Earth's. So, how do we find the acceleration due to gravity on the Moon? Well, it's 1/6, so we'll just divide by 6. So 9.81 divided by 6 gives me 1.63. So, Fg equals 100 times 1.63. We get 163 newtons on the Moon. So, way less on the Moon. That is exactly what we expect to happen. Alright, that is mass and weight taken care of. Number 9. Which has more inertia, a swimming goldfish or a beached whale? If we remember, when we were going through Newton's laws, inertia is directly tied to mass. Inertia is the tendency of an object to want to maintain its motion, and that inertia comes from the mass. So, more mass, more inertia, the beached whale has more inertia, because it has more mass. And thus we get to our actual questions here. So, this is another net force problem we're going to have to use. So, we have a 5.2 Newton force applied to a 1.05 kilogram object, and it accelerates rightwards. The object encounters this much friction, determine the acceleration of the object, and what effect does the friction have on the acceleration of the box. So, from question 10. Question 10, same thing with no friction. So we will ignore the second part here, but I will talk about it. Alright, so how do we find the acceleration of this box? First things first, and that is draw a free body diagram. 1.05 kilograms, we have the normal force going up, force of gravity going down, we have the applied force, which is 5.2 newtons, going to the right, and we have our friction going to the left, in this case FF, which is 3.29 newtons. And I want to find the acceleration. Well, acceleration when I'm dealing with forces comes from my net force equation, F net equals ma, but I don't know what my net force is. So I'm going to have to write an equation to find my net force, and the other net force equation comes from my free body diagram. Net force is everything pointing one direction minus everything in the opposite direction. So right minus left or top minus bottom, depending on which axis we are looking at. This box is accelerating rightwards, which means our net force is to the right, so that means we're going to use right and left. So my net force is everything pointing right minus left in this case. So that's going to be 5.2 newtons minus 3.29 newtons equals the mass, which I know is 1.05, times the acceleration, which I'm solving for. So 5.2 minus 3.29, and then divide by 1.05. Let's do that here. 5.2 minus 3.29 gives us 1.91. Divide by 1.05. We get our acceleration of 1.819 meters per second squared, which is exactly what we are looking for here, rounded up slightly. So that is net force. This front page is our two net force equations. We have the basic F net equals ma, or if we are looking for parts of a net force, when we have multiple forces, not just a single one, we have our expanded net force formula. Everything pointing right minus left if you are in the x-axis, the horizontal axis, or top minus bottom if you are working in the vertical axis, which we will see here on the back. 14. This is going to be another net force question, but instead it will be in the vertical. It is an elevator style question. So we have a 4.4 kilogram bucket suspended by a rope that is lifted upwards from an initial rest position. If the tension in the rope is a constant 83.19 newtons, determine the acceleration of the bucket. So first things first, free body diagram. Always, always, always free body diagram. So 4.44 kilograms of this bucket. We have the tension going upwards, Ft, which I happen to know is the 83.1. 83.1 newtons is going to be the force of gravity going downwards. And typically, for a bucket being pulled up from a well, there's no side-to-side forces, no side-to-side motion, so it's just these vertical ones. And I want to find the acceleration. So, I'm in another situation here. I'm going to need to use my net force formula. F net equals ma, and this is going to get expanded from my free body. In this case, it's the vertical components, because this acceleration is in the up and down of the bucket being pulled upwards. So that's everything pointing up minus everything pointing down equals ma. So 83.1 minus my Fg equals ma. Alright, well, I know my mass is 4.44. I don't know my force of gravity, though. I'm going to have to calculate the force of gravity on this bucket, on this mass. Remember, force of gravity and weight are the same thing. Also remember, mass and weight are not the same thing. This force of gravity is not 4.44. That is the mass of the object. Fg is the weight of the object, the force of gravity. And force of gravity is not 9.81. Force of gravity is the force of gravity on an object, which comes from the equation Fg equals m times g, which we did earlier for the Hitchcock problem. So we're just going to do this to find the force of gravity. Mass times acceleration due to gravity, which is 9.81. So 4.44 times 9.81 gives us our force of gravity, which is 43.55 newtons. So I can then plug this into my equation and solve. So 83.1 minus 43.55 equals 4.44, the mass times the acceleration. So I can now do this. So 83.1 minus 43.55 gives me 39.55 divided by 4.44 gives me my answer of the acceleration equals 8.907 or 8.91. Rounded this up a little too much, but there we go. That is my acceleration of the bucket. So, this is how you deal with elevator-style questions. If you have something in an elevator, if something's being pulled upwards, it works the same exact way as the other net force questions, where something's being pulled sideways. It's just instead of dealing with the sideways motion and friction, we are dealing with the up and down motion with force of gravity and normal force or tension, whatever it happens to be pointing upwards. They work the same exact way. And I hope if you rewind, you're a little stuck on this, rewatching me going through these and explaining will help a little bit. They work the same exact way. Just got to keep in mind, am I dealing with my horizontal or my vertical? And then lastly, I'm going to skip over 15, don't need to worry about it, to one of these, calculating net force just from a free body diagram, especially when you have multiple forces. So, net force on an object just means total force. We just want to find the total force on this object. And we're going to check both our axes. We're going to check the x-axis and the y-axis. So remember, net force is everything pointing up minus everything pointing down. That tells us the total force, the net force for that axis. So net force up and down, 4 up, 4 down, 4 minus 4 is 0. There is no net force in the up and down. They balance each other out. So let's check right and left. Right minus left. So we've got 10 on this side, 6 over here. 6 minus 10 is going to give us negative 4 newtons, or 4 newtons to the left, negative 4 newtons to the left, however you want to phrase that. That is our net force in this case. I'm going to say 4 newtons left, or negative 4. Either way really doesn't matter if it's negative or not. As long as you're specifying it's to the left, we've got it from our free body, we are good. Alright, so there's my net force. Now I just need to calculate the acceleration here, and again, that's going to come from my net force formula, F net equals ma, Newton's second law, and I can just do this real quick. I want to solve for the acceleration, so F net, which is 4, divided by the 15 kilograms, gives me an acceleration of 0.266 repeating to the left. And that's how you calculate net force from a free body. Everything pointing up minus down, or right minus left. Alright, that is essentially it for the forces review. A lot of what we do here is carried over into this next test that we are about to take. So hopefully you find this helpful and can do better on the retest with this information. If you have questions before you take the retest, which, by the way, is through Friday before Thanksgiving, you may go see the other physics teacher, Mr. Mahavik. I will have that information sent out in an email after this video gets posted. If you have questions, please go see him during his office hours. They are essentially the same as my office hours. Before school, after school, or during a block of Mega Lunch, except for Mondays. Alright, good luck on this, y'all. Hope this helps.